Hey everyone, how's it going? Today we're going to talk about circular motion and a very simplified version of circular motion. So let's get started. Let's say there's a bob attached to a string and we kind of twirl it around so it goes in a more or less circle. Alright, so a few things to note here. The velocity is constant, where we assume that it doesn't have to be constant, but for our purposes, we're going to say that the velocity is constant. So if the velocity is constant, I have a question. What's going to happen, or rather, how much time is it going to take for this bob to go through one entire path, one entire circle, one entire revolution? How much time does that take? We call that actually the time period. It's denoted by a capital T. Well, it's very simple to solve for this. It's not too hard. So you can use v, which is the velocity, and no, I did not put an arrow on top of it. When I don't put an arrow on top of velocity, you can think of it as speed or the magnitude of velocity, just a scalar quantity. So velocity is equal to distance over time because I don't have the arrow on top, and the distance in this case for one whole path or one whole circle, that's the circumference of the circle, which is 2 pi r. So let's say that the radius is this little r over here, so that's 2 pi r. 2 pi r. And the time period, which we now denote as capital T, we can just put that in and we've got v. So if we know the velocity, we can solve for the time period, and the time period is 2 pi r divided by v. I want to remember this equation, it's very helpful. Now there's another quantity defined called the frequency, and the frequency is how many of these revolutions occur per unit time. In other words, it's just the opposite or the reciprocal of time period. So you can write the frequency f is equal to 1 over t. I don't know if you can see that over there, so I'll just maybe write it up as well. So f is equal to 1 over the time period. All right, so that's time period for you. Now let's think about something else. Let's think about acceleration for a moment. Do you think that acceleration is going to be constant, it's going to be zero, or it just keeps changing? Well, let's think about this for a minute. I'm going to draw maybe a more neat diagram so it's easier to see this. So we know that it's going in a circular path, right? The bob. And for simplicity, I'm going to just put points for the bob now because it's hard to draw that out and then see the little arrows that I'm going to draw. So let's say that this is where the bob starts off at. So at that point there, I'm going to put an I. That stands for the initial. Okay, so that's where it initially is at. And then after some time, it moves to this area, which I'm going to denote by F, meaning final. Okay, so that's the initial position. The blue is the initial, the red is the final. All right, let's draw arrows out so we can see what that looks like. So I'll just draw an arrow. So this is the position. It looks kind of like a clock, doesn't it? And this is the position here. These are the positions. What about the velocities? Let's draw out the velocities. So the velocities are tangent, right? It's in this direction. So over here it's tangent, so you can actually draw like a perpendicular sort of sign if you want. And that shows that it's tangential to the circumference of the circle. And for F, the same thing. Remember, for vector quantities, we have a direction and we have a magnitude. The blue and red arrows have the same magnitude because the velocity magnitude, which we showed up here, is constant. But the directions are different. So there is some change in velocity occurring, so acceleration cannot be zero. That's the first point I'd like to make. The second point is, how do we find the acceleration, or at least the direction of acceleration, from this diagram? Well, it's not that hard to do. I'm not sure how familiar you are with vectors and how to add and subtract them based on the geometry. I can give you a quick tutorial on that. So if you have two vectors, let's say one direction is like that, the other direction is kind of like that. Or let's make the other direction straight so it's more clear to see what's happening, right? Now, if I want to add these two vectors together, how do I do that? Well, just put one vector following the other. So the first vector, we take it and we just draw it out. And the second vector, which is a straight line, we just put it where the other vector ends. And then the sum of these two vectors is that. This is the answer. The blue line is the answer. So you can see the two little arrows made a big arrow. Now what if you're trying to subtract these two vectors? So instead of saying plus, you're trying to do minus. So let's draw that. Let's say this is a vector, and it's the same vector again. So the same two vectors, we're just drawing them in green. So when you subtract them, you draw one vector, but then you have to reverse the sign of the other vector. So let me try to do that. Just like how in subtraction with numbers, you take 5, let's say 5 minus 1 is technically 5 plus -1, where you're reversing the sign of the second value. So here you have the first vector, which is fine, and the second vector, it's right now pointing towards the right side. We're going to make it point towards the left side. So the answer is this blue arrow here. So what we're going to do above now is the same thing for these two vectors. Remember, acceleration, the definition of acceleration was with a change in velocity divided by time, right? And the change in velocity in this case is v, you can say final minus v initial divided by time. Okay, so let's try to put these two arrows on top of each other. Let's try to subtract these two arrows, the blue arrow and the red arrow, on the circle, because we want to find acceleration's direction. If not its magnitude, let's at least get its direction. And what we're going to do is we're going to move the red arrow on right where the blue arrow is at. So we kind of move the red arrow here. And it's subtraction, so the sign reverses. Okay, so the sign reverses. So the sign reverses, or the direction sort of flips. So where the golden arrow is ending, well, okay, so it's final minus initial, right? So the golden arrow is fine. Actually, the blue arrow's direction has to flip because the negative sign is on the initial one. The final one's fine. So blue needs to flip, all right? So I'm going to erase, or maybe not erase it. Maybe I'm just going to draw it in green. Oh, wow, all right. Okay, let me just do it in green instead. All right, so the direction is this way now. So we're starting from here, going like that. So the acceleration is in this direction. So it's pointing towards the center. So acceleration is towards the center of the circle. By the way, there's a special name for acceleration in circular motion, and this is called the centripetal acceleration. And it always points towards the center of the circle. Now, you can actually test this out yourself. If you draw arrows for velocity anywhere and subtract them, they'll always point towards the center, and they'll always have the same size. So the magnitude of acceleration does not change. But the direction does. The direction always points towards the center. All right? So velocity's direction was tangential, and acceleration's direction was into the circle. For position was actually pointing outward in the opposite direction of acceleration. So just to summarize, so that things are a bit more clear, if this is the path, all right, r, which you can say maybe is the position, and I'll maybe draw a little arrow to show that it's a vector quantity, is always pointing outward for circular motion. And the magnitude of r, which I'm just going to call as r, is constant. Velocity, which I'm going to use for blue, is tangential to the circle, so it's forming right angles with the position. All right, so that's velocity. So velocity is changing, but its magnitude is constant. Now, it's not the same constant, so maybe we'll call it constant 1. It's a different value, of course. All right, acceleration, let me use red. Acceleration is always pointing inward towards the center of the circle, and we call this a centripetal acceleration. So that's A. And the magnitude of acceleration is also constant. And if we know what v is, we can actually find acceleration. Acceleration is equal to v squared over r. I won't be deriving this. I might derive it in a couple of chapters to come, but this is the equation for the centripetal acceleration. And that's the magnitude of centripetal acceleration, because you already know the direction. The direction is always towards the center of the circle. By the way, if you use polar coordinates, r's direction would be r hat. I can't draw up there. Okay, it would be r hat, V's direction, I think, would be minus theta hat. Don't take my word for that. It could be wrong. And A's direction, but it is theta hat, I just don't know if the minus sign is there. And A's direction would be minus r hat because it's pointing towards the center instead of outward, okay? So if you're using polar coordinates and getting comfortable with that, you can verify that that's true. That's what I wanted to explain for circular motion. Now let's go off on a tangent, pun intended. We're going to talk about Kepler's laws, and I'm not going to prove them because that's quite a challenge, but it is fun. I'm just going to, throw them at you and try to explain them so that it's easier to remember Kepler's laws. And these are Kepler's laws of planetary motion. So yes, it's about the solar system. The first law says that the orbits of all planets are ellipses, where the sun is at one of the foci. If you don't know what an ellipse is, it's just an elongated circle. That's a bad, okay. That's just an elongated circle. And the foci, there are two foci to an ellipse. The sun is at one of them. And this is the planet's orbit. So that's our Earth, maybe pretty big, right? And it's just going around in this elliptical orbit. So that's the first law, Kepler's first law. And this was a big deal because people at that time thought that all the planetary orbits were actually circles. And so when he found that it was an ellipse, it was unbelievable, but all the calculations started making sense. So it was an interesting time. All right, the second law says that when a planet travels in an orbit, an imaginary line connecting the planet and one of the foci sweeps equal areas in equal intervals of time. Now I know you probably think, what? So let me just draw it out. So let's draw a nice ellipse here. Let's say that this is our sun and this is the Earth. So let's say that the Earth goes from this area to this location, and we had to draw now an imaginary line that connects the Earth and the sun. So maybe I'll use gold for that. So, all right. So let's say this time that it went from, this position to the next one, with that time is t. And the area that it sweeps is this area here. All right, I'll just call it A. Now let's choose another location. Let's say the Earth is now here, and then it moves again in the same time period. Let's say it moves here, okay? And then we have another area. Now what Kepler's law is saying is, Kepler's second law is saying the golden area and the green area are equal if the golden T and the green T are equal. So it sweeps equal areas in equal times, this imaginary line that connects the Earth and the sun. So even over here where the orbit, let me draw maybe one more. Even over here, where actually the Earth will move faster since it's closer to the sun, even this area will be equal to those. So if time period is same. Or not the time period, but just the time. All right, so that's what Kepler's second law says. All right, so that's the second law. The third law is very easy. The third law says that the time period to complete an orbit, the square of that is directly proportional to the cube of the radius, taking the radius cubed. So in other words, you can write t squared is equal to some constant a times r cubed. I don't know what a is. Okay, it's not the area. It's just some constant that you can calculate. So if you get a question that says that what happens to the time period if the radius, let's say, doubles? Well, all you have to do is plug in, r becomes 2r, so just plug that into the equation. And you can keep the a, if you want, you don't have to. You can write t squared is directly proportional to r cubed. So now that becomes t squared is directly proportional to 2r cubed because we substitute r with 2r, right? And now this is 8r cubed. So now if I take this 8 has to do with how t changes, right? So this is square, so we take the square root on 8, and that means t changes by the square root of 8, which I believe is 2 root 2, right? So that's how t changes. So it changes more than double. This is directly proportional to the radius. And another way of thinking about this is, as you increase the radius of an orbit, the time period is also going to increase, and the exact amount by which it increases is this relationship. All right, so that's all it means. It's just saying something that's already obvious and giving us more information. It's already obvious that if you increase the radius of a planetary orbit, the time period is going to go up. It seems intuitive. So by what quantity? Well, that relation. Well, this isn't entirely true, but it is true when we're just approximating, okay? So this is Kepler's third law. So it's very simple. Now we're going to move on to another topic, maybe one that's closer to our hearts. This is a topic of universal gravitation. So we already talked about gravitation on Earth, right? If you remember what gravitational force was on Earth, we said F is equal to mg, where g was the acceleration due to gravity. But now we want to look at gravity on a larger scale, on the astronomical scale, or even for very, very tiny quantities. Let's think about the Earth and the Sun. What's the gravitational force between the Earth and the Sun? This equation can't tell us that. We need to derive an equation for universal gravitation. And by the way, this is Newton's law of universal gravitation. So the law says that the force of gravity, which I'll call as Fg, is directly proportional to the product of masses. So let's say your first mass is m1 and your second mass is m2, and we're doing the product between them. And it's inversely proportional, meaning it doesn't really like this, it goes oppositely, to the distance between those two objects, which I'll just call as r. And not just the distance, the square of the distance, so r squared. And they're proportional, so I can put the proportional sign, but I don't want to draw the proportional sign, I'll just make an equal and put a constant. Now this constant here that I drew is called the universal gravitational constant, and it has a value of 6.67 into 10 to the power negative 11, and its units are Newton meter square per kilogram square, and you can easily verify that by just moving things to the other side, right? Newton meter square, and then divided by 2 masses, so 2 kilogram square, right? This is a very important constant, by the way, the universal gravitational constant. So if you want to calculate the gravitational force between any two objects, find out what their masses are, find out what the distance between them is, and just plug it into the equation. Very simple. All right, so let's talk about where this applies and where this doesn't apply. This applies for point objects, tiny objects. Now, do point objects exist in reality? No. So they can approximately apply in situations where the radius of these objects themselves, meaning the size of these objects, is small compared to their separation. For example, let's say this is the sun, and let's say this is the earth. Now, they each have radius, right? They have a radius, this has a radius. But that's small compared to the distance between them. So we can use this law to describe their gravitational force. Now let's say we have two objects that are very close together and they're very big. All right, so in this case, the separation is very small compared to their own radii. So we can't use the gravitational force, Newton's law of gravity. We might have to make it a bit more complicated and then use it. So we won't, but for our purposes, we will have situations like this. We will not have situations with big objects. All right? Now looking at this equation, how does it collapse to this one, right? How does it simplify to this specific situation? Because this was only for Earth, if you remember. And this is the universal law, the one that I just drew out with g m1 m2 divided by r squared. This is the universal law. So how do we simplify the universal law to apply on Earth? Well, it's very simple. Let me show you how. So remember, Fg was equal to g. Let's write g better. So g m1 m2 divided by r squared, right? Where r was the distance. Now for any object on Earth, so let's say this is Earth, and there's a little object on top of it. And we want to calculate what's the gravitational force between this object and the Earth. Okay, so g is still g, m1, let's say it's the mass of the Earth, and let's say m2 is just m, it's the mass of this little object over here. And it's all divided by r squared. Now obviously any object, it's not exactly sticking to Earth, right? It could be a little up like a parachute. In this case, we would have radius of Earth to be one part of the distance, and then the height of the object itself to be the additional part. Now for most objects that are close to Earth, the radius of the Earth is always a lot bigger than the height or how above Earth it is. So if you're sitting on a chair, for example, that additional height that makes you above Earth's surface is very small compared to this radius. So remember, r is equal to the radius of the Earth plus h, but we can approximately say that it's just the radius of the Earth because the radius of the Earth is so big compared to the height. So instead of having this little r square, I can write re square. Now all three of these are constants. And if you do the math, guess what they become? They become g. So that's where your mg comes from. So g, the acceleration due to gravity, is actually three constants combined. Isn't that cool? And for every planet, it's always going to be something different because they have a different mass and they have a different radius. So on the moon, this g is smaller because its mass maybe is less and its r square is smaller, and the way that it all comes together makes it smaller than the Earth's acceleration due to gravity. So that's the gravitational law, the universal gravitational law. One note, there are different types of satellites that the Earth has. We call it, there's natural satellites or artificial satellites, but that's not what's important. What's important is the geostationary one. And the reason why I'm talking about geostationary ones is this is a favorite question for a lot of physics exams. Geostationary means that if you're looking at the satellite, let's say you're on Earth and you're looking at a satellite. And for those who don't know, a satellite is just one of those weird objects that you can see while you're on Earth. That's in Earth's orbit. So the moon, for example, is a satellite. It's a natural satellite. An artificial satellite would be, one of those big dishes, or the International Space Station, something man-made. All right. Now let's talk about the geostationary satellite. The geostationary satellite is one that doesn't seem to be moving. So if you're on Earth and you're looking at the satellite, it's not changing its position. It's always maybe just right above your head or right to the east. It's never moving. It doesn't appear to be moving. That's because its time period is 24 hours. And this is what's going to help you solve the exam. All right? Because they're probably going to ask you to calculate the velocity or something. And they're not going to tell you the time period is 24 hours. That's something you're going to have to know from the fact that it's geostationary. So they'll tell you it's geostationary, and they might tell you to calculate something, and they won't tell you the time period is 24 hours. So that's something you're going to have to know by the definition of what a geostationary satellite is. All right. I just thought about putting that in. Well, that's really it. That's all I have for circular motion. There's not a whole lot, and that's because the chapter that covers the real, circular motion or all the fun equations is actually rotational motion. Circular motion is just a brief introduction of Kepler's laws and the law of gravity and whatnot. It doesn't really have a lot of content, so I'm just going to leave it at that. And I'll see you next time.